Okay, so we're finding an area again here between two curves, and they tell us the curves are x squared, which I've already sketched out, and the second one is just a flat line at 1, which I can probably draw without too much trouble. Looks like that. Now, they say between the intersection points, but we would have figured that out anyway. The only area that's bounded by these two curves is the area in here. This area extends forever, and so does this area, and so does this one up here. So there's really no way we could, these areas are infinite because they aren't bounded on every side. This is the only area that's contained. It's got lines all around it, and so if they said find the area bounded by these two curves, the only choice we would have is this area in here if we expect to get a finite answer. So we should be able to do some kind of integral thing to get this area. How is it going to look? There's an integral sign. We know that the heights of these rectangles are going to be their top minus their bottom, and in this case the tops of these rectangles are all 1, and the bottoms for each of these rectangles are the x squared curve. So 1 minus x squared is our integrand. We need a dx or else this isn't a real integral. And now we need limits of integration. What are our bounds on the left and right? Well, those would be the places where x squared intersects with 1. So we'll just solve a quick equation here. If x squared equals 1, you might be able to just eyeball this and see that the answer is x equals plus or minus 1. Or the correct way to do this is get an equation that equals 0, subtract 1 from each side, factor this, x plus 1, x minus 1 equals 0, and lo and behold, that gives us x equals negative 1 or x equals 1. So those are the coordinates of these two intersection points, and those are our limits of integration. We'll begin at negative 1, we'll integrate up to 1. Okay, so if we're doing this, we need an antiderivative for 1 minus x squared. The antiderivative of 1 is x. The antiderivative of minus x squared is minus 1/3 x cubed. Increase the power of x by 1 and then divide by the new power. We could put a plus c on here, but we know what's going to happen. It's going to cancel when we do our subtractions, so probably not worth it. And we're integrating between minus 1 and 1. So 1 minus 1/3 is what happens when we plug 1 into that. If we plug in negative 1, we get negative 1, and then, let's see, negative 1 to the third is negative 1, times 1/3 is, times negative 1/3 is positive 1/3. So this cleans up to 1 minus 1/3. Minuses cancel, and we get another 1, and then we get another minus 1/3. So 3/3 plus another 3/3 is 6/3, and then we lose a third, we're down to 5/3. We lose another one, we're down to 4/3. The total area in here should be 4/3. A quick aside, sometimes you can use symmetry to make your work a little easier when you do an integral like this. Do you find it believable that this region and this region on the right are identical, that they're mirror images of each other? Well, they are, and you can prove that by checking that this function and this function both have even symmetry, meaning their left side and right side are identical. If that's true, then instead of integrating from minus 1 to 1, another option that you would have is to integrate from 0 to 1. Just find the area of the right-hand piece, and once you get that result, double it. So for a symmetric function, integrating half the function and then doubling the result can give you the same result as integrating the whole thing. And that can be nice with expressions like this, where plugging in a 0 is a little easier than plugging in a minus 1. It's not a big difference, but if you ever see someone doing this, now you'll know what's going on, and you might even find you like this approach, that it saves you a little bit of time.